So we're doing problem 62, which is a red problem. So okay, the book gives you a drawing that looks like this. They just label x like a distance from the end, and then L is just the equilibrium length, and then so there's a block of mass m connected to a spring, and it's in simple harmonic motion, and there's dx, which is like a infinitely small x, which we'll use later. Okay, so the problem asks you to find the kinetic. The problem asks you to find the kinetic energy of the entire system, and which is the kinetic energy of the spring and the mass of the block. So K total equals K of the block plus K of the spring. And then so for the spring, what you have to do to find the kinetic energy of the spring is sum up all the kinetic energies of the infinitely small x's. And then the K of the block, you just do 1/2 mv squared. Okay, so this is 1/2 mv squared. Actually, I'll make this a big M. And then this is, okay, so what you have to do is, to sum up all of the kinetic energies, it's basically an integral. So you sum up all of the dk's, which is each infinitely small k. So you have to find the derivative. So dk equals 1/2. Oh, I forgot to mention, the problem also gives you these things. They just give you the formulas, and so that's it. So what you have to do is find dk, or find the derivative, which is 1/2 dmv squared. Yeah. And then so the problem gives you these things, so you have to plug it into there. So this becomes 1/2 m over l dx times x over l v squared. And then, I don't know, I guess I'll simplify that. You know what? Later. Okay. So this k is all of the infinitely small k's added up. It's an integral. So we take this and then put it here, but it's like summing up each k. So we're integrating from 0 to L, 0 being here and then L being the distance, the equilibrium position of the block, the spring. And then basically I'm just taking this and putting it here. So wait, there's an ML here. dx. Okay. And then you have to solve that integral, so so these are, everything is constant except for the x, so I'm just gonna move it out front here, and then do this for x. And after you know how to plug this in, I'm pretty sure, because you're in physics C. So you just plug in the L and the 0, and then after you do all of the math, this will become 1/3 mv squared. Yeah, like that. Ow. So if you simplify this, you'll get 1/2 big M plus 1/3 m v squared, and then that is the kinetic energy of the entire system of the spring and the block added together. All right. Then the problem asks you let's see. Then the problem asks you to find the period. And then what you have to do first is find omega and then plug it into the formula and then to get tension. The period. So, yeah, we'll find omega first. The force acting on the block is force of the spring, which is this, and then that's equal to MA. And then A is the same thing as the second derivative of position. And then we'll just, do some algebra. So this M comes to the other side. Now, so then we have something times position times the second derivative of position. So this something becomes omega squared. So omega equals square root of k over m. And we found m. This is m, like we found it in part A. So m is big M plus 1/3 little m. So wait, big M plus 1/3 m. So it's like that. So this is omega, right? And then there's a formula, omega equals 2 pi over the period. That's right. So this is equal to 2 pi over the period. So then the period is equal to 2 pi m plus 1. We just did some algebra to find